Today we'll be talking about kinematical equations. All of you have studied these equations. I'll just write them down here so you will immediately realize that these are kinematical equations. V equal to V naught plus AT, or X equal to X naught plus V naught T plus half AT squared, or V square minus V naught squared equal to 2AX. These are those equations. You have already studied them. I want to derive them for general purposes, not for the particular one-dimensional motion, not for particular constant acceleration. I want to derive them for general motion. And if I know them for general motion, I know them from everything. Okay, I know them for every motion possible. And we'll take these guys as special cases of that general case. Okay, yes. So let's move and figure out first kinematical equation. Kinematical equations are not something out of the world. They are something very simple, just as this equation. This is one of the kinematical equation. dv by dt equal to a, this acceleration. This is the definition of acceleration, which is the first kinematical equation by itself. This definition of acceleration. But we don't define this guy as the kinematical equation. Rather, we do something like this. A dt, and we take integration both sides on the limit v naught vector to v vector dv equal to from time t naught to time t a dt. Okay, and if you see this closely, if you observe this closely, you can write it down as something like this: v vector minus v naught vector equal to a integration at a dt from t naught to t. Here, this is the first kinematical equation. This is the first kinematical equation. Here, acceleration is a function of time. Okay, velocity v bar is velocity at t, at time t, and v naught is velocity at time t naught. These are the definitions of the term. Acceleration can depend on time. That means at this time there is some different acceleration, this time there is some different acceleration. We are not talking about constant acceleration. Acceleration can depend on time. So we are not solving this integral, we are just keeping it as it is. And this is our first kinematical equation in most general form. Okay, you can see this is very simple, very simple. Okay, and now if you want to dig a little bit deeper, this is first kinematical equation of motion. If you want to dig a little bit deeper, what you will realize is the definition of velocity in itself contains one kinematical equation. So definition of velocity is dr vector by dt. Change in position with respect to time is velocity. Okay, so change in position vector with respect to time is velocity, and from this we can actually derive similar way. We can derive r vector minus r naught vector equal to integration t naught to t v dt, where we should again define that r vector is position vector at time t, r naught vector is position vector at time t naught, and v is a function of time t. Velocity is also a function of time t here, so we cannot take it out from the integral because it may be some function of time. Are you guys following these integrals and all those things, or you guys are not following these integrals? So one way of looking at it is, I can break this for one, I can see this for one component. So you can see this for dx by dt equal to ax. Then you find out, you realize that ax is also a function of time, can also be a function of time, and you can find out, sorry, dvx by dt. You can realize this one equation, you can solve it like this, and you can then realize that since all three equations will be same, so vector equation will also be the same. That is one way of looking at it, but I'll directly use the vector notations. Are you guys getting what I'm doing here, or it is too hard mathematics?
So we are getting. I
You
get
are
it.
getting? Okay, so just as we discussed, differentiation of a vector means differentiating each and every component, right? differentiation of vector does not mean anything different. It is differentiating each and every component. But let me just clear a misconception right now, right here, that whenever we are talking about, suppose, spherical coordinates. So spherical coordinates versus Cartesian coordinates. Here is the difference. In spherical coordinates, r vector is written as dr r cap plus r d theta theta cap plus r sine theta d phi cap. I think you studied this in Prakhar Bhai's class, or you did not study this?
Yes, sir, we did it.
Yes. So this is small dr. For Cartesian coordinates, the small dr is dx x cap plus dy y cap plus dz z cap. This is small dr in Cartesian coordinates. Now, if you are differentiating this with respect to time, suppose, then something beautiful happens. Here, if you differentiate with respect to time, so you differentiate both sides with respect to time. Okay. So if you just remove d from all the sides, it is just basic equation r theta and sin theta phi. Just remove the d from both sides, so it becomes easy to visualize. That's all. Okay. Okay. So now if you are doing dr by dt here, this was r. Now if you are doing dr by dt, you are doing d by dt to both of these guys. D by dt to both of these guys, multiplication of both of these guys. Okay, it is x into x cap. So ideally it should be dx by dt into x cap plus x times dx cap by dt. This should be the ideal first term. Here also the ideal first term will be dr by dt into r cap plus dr cap by dt into r. This should be the ideal first term. But here what happens, you know that this is unit vector in direction of x cap, so its magnitude is fixed, its direction is fixed because direction is x cap in x direction. Magnitude is 1 unit vector. So this guy is 0 immediately because it is not changing with time. But here, if you'll see, the radius vector, the r cap vector is different here, r cap vector is different here, r cap vector is different here, r cap vector is different here. So if particle is moving and going to any point, this will not be 0 always. So you need to consider both of the terms here. Okay. So actual velocity in this spherical coordinates will be different. It will not be directly dr by dt r cap plus differentiation of this plus differentiation of this. It will be differentiation of these unit vectors as well. Okay. What does it mean, or what is the value of the velocity after that? We'll talk about that in the next week. Okay. But this is what it means. Don't directly just assume that r cap is same, because r cap is different at different points in the space. Okay, r cap is always radially outwards. A unit vector pointing radially outwards, and radially outwards is not a unique direction. It is different for different parts. Okay, it is not a unique direction. If we talk about Cartesian axis, from reference point of Cartesian axis, this r cap is not a unique direction. Okay, so if you are here at r cap, here at r cap is changed with respect to time. So particle moved from there to there, r cap has changed. Okay, so that's why dr cap by dt is there. It is not directly zero. So that this was a common misconception that I wanted to clear right now, right away. But yes, this is kinematical equation number 2 actually, but we don't call this equation number 2. We still dig deeper and we still figure out that we can write it as v naught plus integration a dt. So we can write this v as v naught plus integration a dt. So in the end, we can write r equal to r naught plus integration t naught to t, and v, what should we write v? It is v naught plus integration t naught to t a dt, and there is extra dt. Can you see this happening from equation number 1?
Yes, sir.
Yes. So here you know all the terms r naught, v naught, a is also a function of time. V naught is not a function of time here. So this equation you can write down again in a much more simplified manner. That is R equal to R naught plus V naught and integration dt. So it is V naught dt. If you see, it is V naught vector integration dt, which is t minus t naught, plus now this a is also a function of V naught was not a function of time because it was a velocity at some time t naught, a fixed value, not a function of time. We took it out of the integral. Then we integrated t naught to t dt, this dt. Then there is additional term which contains now two integrals, t naught to t and t naught to t again. And now it is a dt into dt. This is now second equation of motion. This is now second equation of motion. Okay, so if you see closely, this is very complicated looking equation, but it is not coming out from something very peculiar. It is coming out from the simplest definition of velocity. Okay, so this is ideally the second kinematical equation. This is the first kinematical equation, but for our purposes, we generally simplify these guys. Generally try to simplify these guys. We try to take special cases. This is the most general case, but we try to take the special cases. Okay, so what is the special case? Number one, for constant a, if a is constant, what was the equation number one? It was v naught plus integration t naught to t adt. So if a is constant, that is not function of time. What do we mean by constant here? It is not a function of time. Constant in time. A is now not a function of time. So in that case, you can take it out of the integral. You can solve this integral very easily. V equal to v naught plus a t minus t naught. Where t naught is some initial time and t is the time at which we are finding this velocity. So this is at time t. This is the value of, this is the vector of velocity at time t. This is the vector of velocity at time t naught. And this is acceleration, which is constant. Okay, so this is first kinematical equation for constant a. Second kinematical equation will immediately change into some simplified form, that is r naught plus v naught times t minus t naught. This was already there, plus since a is constant, so a we take it out. We do the first integral, that is t minus t naught. Then the second integral remains. There were two integrals here. So first integral we did a, we took out common, and then integration dt is t minus t naught. So we did it. There is another integral waiting for it to be done, and that is r naught plus v naught into t minus t naught plus a vector. And now if you integrate this, it becomes integration of t is half at square minus the integration of t naught is, it is not half. Integration of t naught is something simple than that. It is a t naught t. This is the integral of t naught. But if you put, okay, a little bit harder integral to solve in terms of just algebra, nothing else. So I should not write it directly here. What I should do instead is should keep a vector out and out for the whole process. It is t square by 2 minus t naught into t. Now you can put both the limits, r vector plus v naught vector t minus t naught plus a vector. And now if you put t here, so it is t square by 2 minus, if you put t here instead of t, it is minus t naught t minus t naught square by 2 and minus minus plus t naught square. So now if you will add all of them, which will give you a very simplified equation. This is r naught. This is still not simplified. I know. You will be asking, sir, why you are doing all of this? Are we going to use it someplace? I don't know. But what I know is you should know the most general form. you should not only remember these equations, because these are for anyways for constant acceleration. You should not remember these guys as well, because you can derive them from the basic definition of velocity or position. Okay, acceleration and velocity, you can derive them from basic definitions, so you should not remember those. You should not remember those. Something you should remember, but you should remember with conditions, is next three equations.